Hello everybody, I welcome you all to my fifth lecture on DC transients. In my previous 4 lectures, we have seen introduction regarding DC transients and initial conditions. We have also solved tutorials on initial conditions. We have derived the complete response expression for series RL circuit in both differential and Laplace transform method, and we have also solved some tutorials on series RL source free and source driven circuits using differential method and Laplace method. So in today's lecture we shall continue solving some more tutorials on series RL circuits using differential equation method and Laplace transform method. For the sixth example, for the circuit shown, find the expression for currents in both the loops. So here the switch is being operated at t is equal to 0 seconds. So after the switch is closed, we have two meshes. So before the switch is being operated, for t less than 0, since it is open, the current flowing in both the meshes will be 0. So I1 of 0 and I2 of 0 will be 0 amps. So since both the meshes have inductor, obviously 0 plus and 0 minus, both values will be 0. So next, for t greater than 0, we have to find the expressions in both the loops. So let us try to do this sum in Laplace domain. So therefore, when I apply KVL, then I get 5 into I1 of t plus 1 into di by dt plus 10 into I1 of t minus I2 of t is equal to 100. So the second equation is nothing but 3 into di2 by dt plus 20 into I2 of t plus 10 into I2 of t minus I1 of t is equal to 0. So when I apply Laplace transform, this becomes 5 into I1 of s plus s into I of s minus I of 0 plus 10 into I1 of s minus I2 of s is equal to Laplace transform of constant is by s. So when I simplify this value anyhow is 0. So when I simplify this, it is 15 10 plus 5 plus s into I of s minus 10 I2 of s. Okay, this is I1 of s is equal to 100 by s. So the first equation after simplification will become 15 plus s into I1 of s minus 10 into I2 of s is equal to 100 by s. I'll consider this as equation 1. So after applying Laplace to this equation, this becomes 3 into s into I2 of s minus I2 of 0 plus 20 into I2 of s plus 10 into I2 of s minus I1 of s is equal to 0. So I2 of s value is also 0. So Upon simplification, I get minus 10 I1 of s plus 30 plus 3s into I2 of s is equal to 0. So the second term, I2 of s coefficient is here 3s, and here I have 30, so it is 30 plus 3s. So we have obtained two equations. So now if I want I1 of s, it is nothing but delta 1 by delta, and if I want I2 of s, it is delta 2 by delta. So we all know how to solve sums using Cramer's method. So delta will be nothing but the coefficients of both the equations. So in first equation, I1 coefficient is 15 plus s, I2 coefficient is minus 10. So 15 plus s minus 10. I2 in second equation, I1 coefficient is minus 10 and I2 coefficient is 30 plus 3s. So if I cross multiply, I will get 15 plus s into 30 plus 3s minus 100. So if I simplify, I will get 3s square plus 75s plus 350. So this, if I find the roots, I can write this as s plus 6.2 into s plus 18.79. So similarly delta 1. So in this, the first column I should replace by the coefficient of right hand side terms. In first equation, the right hand side value is 100 by s, and in the second equation, the right hand side term is 0. So delta 1 will be 100 by s, 0. The second column remains the same, minus 10 and 30 plus 3s. So if I cross multiply, then I will get 100 by s into 30 plus 3s. Similarly delta 2 will be, the first column will remain as it is, 15 plus s and minus 10. The second column should be replaced by right hand side term, that is 100 by s and 0. So if I cross multiply, I will get 1000 by s. So therefore I1 of s is equal to delta 1 by delta, that is 100 into 30 plus 3s divided by s into s plus 6.2 into s plus 18.79. By using partial fractions, we have to find the values of a, b and c. So a by s plus b by s plus 6.2 plus c by s plus 18.79. So after simplification, the ABC values that I get is a is equal to 25.75, b is equal to 14.6 and c is equal to minus 11.14. So on substitution of this equation, I1 of s will be nothing but 25.75 by s plus 14, oh sorry, this is minus 14.6, so it is minus 14.6 by s plus 6.2, this minus 11.14 by s plus 18.79. So on applying inverse Laplace transform, I1 of t is equal to inverse Laplace of 1 by s is anyhow 1, so it is 25.75 minus 14.6 into inverse Laplace of 1 by s plus a is e power minus at, so e power minus 6.2t minus 11.14 into e power minus 18.79t. So this is the expression for the current flowing in first mesh. Similarly, I2 of s is delta 2 by delta, so there is nothing but delta 2 I have got as 1000 by s, so it is 1000 divided by s into s plus 6.2 into s plus 18.79. So here also if I apply partial fractions, it is, let us consider a1 by s plus b1 by s plus 6.2 plus c1 by s plus 18.79. So on simplification, I will get the values a1 to be 8.58, b as minus 12.81 and c to be 4.22. So I2 of s becomes 8.58 by s minus 12.81 by s plus 6.2 plus 4.22 by s plus 18.79. So on applying inverse Laplace transform, I2 of t is equal to 8.58 minus 12.81 into e power minus 6.2t plus 4.22 into e power minus 18.79t. So this is the expression for the current flowing in second mesh. Let us consider the seventh example. So find the current I of t for t greater than 0 for the circuit shown. So here you can see there are two switches. First switch is operated at t is equal to 0 and the second switch is operated at t is equal to 4 milliseconds. So remember, if your sum consists of two switches, then in this case also you will have to consider the expression of current in three cases. So here also first case is for t less than 0, second one when t is in between 0 and 4 milliseconds, and the third case is when t is greater than 4 milliseconds. So initially the switch is opened for t less than 0. So obviously this switch, by the position of the switch I can say that initially this switch is closed and at t is equal to 4 milliseconds this switch is opened. So at t less than 0, since this circuit is open, I of 0 minus is nothing but 0 amps. But due to the property of inductor, as it does not allow any sudden changes in current, this is also equal to I of 0 plus. So next, when t is in between 0 and 4 milliseconds. So when t is in between 0 and 4 milliseconds, this switch S1, let us consider, is closed, and even this switch S2, let us consider, is also closed. So let us draw the circuit when the time is in between 0 and 4 milliseconds. So we'll have a voltage source 100 volts. Since the switch is closed, we'll get a resistor 50 ohms. Since this is short circuit, the 100 ohm resistor will not be playing any role in this circuit. So therefore you'll get an inductor of value 0.100 millihenries. I can write as 0.1 henries. So let us consider this as I of t. So let us find the expression for I of t in this interval. Since it is source driven, I of t is equal to I of infinity plus, your initial value is anyhow I of 0. So I will consider I of 0 minus I of infinity into e power minus t by tau. So when this circuit is at steady state, the inductor will act as short circuit. So I of infinity will be 100 divided by 50, which is 2 amps. And tau value is nothing but L by R. L value is 0.1 and R value is 50, that is 1 by 500. So let us substitute all these values in the general expression. So I of t is equal to I of infinity, which is 2, plus I of 0 is anyhow 0 minus 2 into e power minus 500 t. So therefore I of t is equal to 2 into 1 minus e power minus 500 t amps. So this is the expression for current in between the interval 0 and 4 milliseconds. So before we find the expression for current for t greater than 4 milliseconds, let us find the value of current at t is equal to 4 milliseconds. So substitute t is equal to 4 milliseconds in this expression. So I will get I of 4 milliseconds is equal to 2 into 1 minus e power minus 500 into 4 milliseconds. So when I simplify this, I'll get the value of current at 4 milliseconds to be 1.729 amps. So next, for t greater than 4 milliseconds. So when the t is greater than 4 milliseconds, the switch S1 is anyhow closed and switch S2 is opened. So when this switch is opened, we will get the resistance value to be 150 ohms in the circuit. So the circuit will consist of a voltage source of 100 volts in series with a resistor of 150 ohms and inductor 0.1 henries. So since this is again a source driven series RL circuit, the general formula I of t is equal to I of infinity plus, instead of I of 0 I should consider I of 4 milliseconds, since it is the initial value at this time interval. Milliseconds minus I of infinity into e power minus, instead of consider t by tau, since we are considering t greater than 4 milliseconds, so it is e power minus t minus 4 milli by tau. So I of infinity, when this circuit reaches steady state, I of infinity will be 100 by 150, which is 0.66 amps, and the time constant tau is L by R, which is L value 0.1, R value is 150. So this I can write 1 by 1500. So substituting all the values, in the general expression, I of t is equal to I of infinity, which is 0.66 plus I of 4 milliseconds 1.729 minus I of infinity, which is again 0.66 into e power minus tau value is 1 by 1500, so 1500 into t minus 4 millis. So on simplification, this expression becomes 4 milli I can write as 0.4. So it is I of t is equal to 0.66 plus 1.069 e power minus 1500 into t minus 0.4. This is the expression of current during the interval t greater than 4 milliseconds. So the next 8th example is asked to find the expression for current I of t for t2 is equal to 2 seconds as well as when t is equal to 5 seconds. Here we have two switches. The first switch is initially open and is closed at t is equal to 0. Here the second switch, it is opened initially and this switch is closed at t is equal to 4 seconds. So here also, since we have two switches, we will have three cases. First one is t less than 0. Second one when t is in between 0 and 4 seconds. And the third case is when t is greater than 4 seconds. So when t is less than 0 seconds, since this is open circuit, I of 0 will be anyhow 0 amps. So when t is in between 0 and 4 seconds. So let us redraw the circuit. When the time is in between 0 and 4 seconds, I'll have a voltage source of 40 volts in series with 4 ohms, and since this is open at t is equal to 0 and 4 seconds, this branch is open, so you will have a 6 ohm resistor in series and an inductor of 5 henries. So since this is a source driven series RL circuit, the expression I of t is nothing but I of infinity plus I of 0 minus I of infinity into e power minus t by tau. So when this circuit reaches steady state, inductor acts as short circuit. So I of infinity in this case will be 40 by 10, which is 4 amps. And the tau value will be nothing but L by R, which is 5 by 10. This 1 by 2. So let us substitute all these values in the general expression. So I of t is equal to I of infinity is 4 plus I of 0 is 0 e power minus 2t. So I of t is equal to 4 into 1 minus e power minus 2t amps. So this is the expression for current in the time interval 0 and 4 seconds. So before we derive the expression for current for t greater than 4 seconds, let us substitute t is equal to 4 seconds in this above expression. So I of 4 will be nothing but 4 into 1 minus e power minus 2 into 4. So on substitution, I of 4, that is the value of current at 4 seconds, is nothing but 4 amps. So for t greater than 4 seconds, this switch is closed as well as this switch is also closed. So we will get two meshes. So for t greater than 4 seconds, let me draw the circuit. We will have 40 volts in series with 4 ohms in series. So here you will have the parallel branch 2 ohms in series with 10 volts. Again here have a 6 ohm resistor and an inductor of value 5 henries. So here, since I have two meshes, let us consider this to be I1, and in this let us consider to be I2. So since it is a source driven series RL circuit, so I of t is equal to then I of infinity plus, here instead of I of 0 I should consider I of 4, I of infinity into e power minus t minus 4 by tau. So I of infinity, when this circuit reaches steady state condition, the inductor will act as short circuit. So at when t tends to infinity, get a circuit as 40 volts in series with 4 ohms. You will have an resistor 2 ohms in series with a voltage source of 10 volts. Here are a resistor 6 ohms, and here instead of inductor I had to replace by short circuit. So this is nothing but I of infinity. See, this is I1, this is I2. So I2 will be nothing but I of infinity. So let us apply mesh analysis and find the value of I2. So if I apply mesh analysis, it is 4I1 plus 2 into I1 minus I2 plus 10 is equal to 40. So on simplification, I get 6I1 minus 2I2 is equal to 30. I will consider this as equation 1. So second mesh, when I apply KVL, so it is 6I2 minus 10 plus 2 into I2 minus I1 is equal to 0. So on simplification, I will get minus 2I1 plus 8I2 is equal to 10. I will consider this second equation. So on solving 1 and 2, I will get I2 to be 2.727 amps, which is obviously equal to I of infinity. So the tau value is L by R. L value is 5 henries, and here since we have many resistors, we have to find R equivalent for this circuit, equivalent across the inductor terminals. So therefore the tau value will be L by R equivalent. So while finding R equivalent, I had to replace the voltage source by short circuit. So I have 4 ohms resistor, here I have 2 ohm resistor, I have 6 ohm resistor. So here this voltage source I have replaced by short, here another voltage source I have replaced by short, and we have to find the value of R equivalent from the inductor terminals. So these two are in parallel, so R equivalent will be 4 into 2 by 4 plus 2, and that value is in series with 6 ohms. So when I simplify, I will get 7.33 ohms. So next, tau will be nothing but L by R equivalent, which is 5 by 7.33, which is nothing but 0.68. So therefore, substituting all these values in the general expression, I of t is equal to I of infinity, which we have got 2.727 plus I of 4 seconds, which we have got as 4 amps minus 2.727 into e power minus t by 4 by 0.68. So therefore, on simplification, I of t is equal to 2.727 plus 1.273 into e power minus, so 1 by 0.68 will give me 1.46 into t minus 4. So this is the expression for current flowing to inductor when t is greater than 4 seconds. So in the original sum, it has asked us to find the value of I of t for t is equal to 2 seconds and t is equal to 5 seconds. So for t, remember that this expression, we have two expressions for current. This expression is valid for t in between 0 and 4 seconds, and this expression of current is valid when t is greater than 4 seconds. So you asked us to find the value of current at t is equal to 2 seconds and t is equal to 5 seconds. So for t is equal to 2 seconds, we have to consider this expression. Substituting t is equal to 2, we will get I of 2 is equal to 4 into 1 minus e power minus 4, which will give me 3.93 amps. So I also want I at 5 seconds. I have to consider the second expression. So 2.727 plus 1.273 into e power minus 1.46 into 5 minus 4. So on simplification, I'll get I of 5 to be 3.02 amps. So in my next lecture, we shall continue solving some more tutorials on series RL circuits using differential as well as Laplace transform method. Thank you.